In this video, we will study alternating current circuit. In an AC circuit, there are three important components which includes resistor, inductor and a capacitor. Now let's discuss the alternating current through resistor. For a resistor in an alternating current circuit, the voltage V and the current I are in phase. This means that they reach their maximum and minimum values simultaneously. The mathematical expressions for voltage and current are these. Here V0 and I0 are the peak values of voltage and current respectively, and omega is the angular frequency. Remember that if the voltage increases or decreases, the current does the same since they are in phase. This direct relation is due to Ohm's law for AC circuits, where V is equal to IR. For the power dissipated and the resistor, the formulas provided for power are these. These formulas are valid when the voltage and current are in phase. The power in a resistor is always positive and fluctuates between 0 and maximum value. Now let's discuss the alternating current through the capacitor. We know that there are two types of current, alternating current and direct current. When we have the direct current, the capacitor behaves as insulator as it only stores charge. But when we have alternating current, the capacitor behaves as conductor. In a capacitor, if we want to measure the charge on parallel plates, we can use the formula which is Q is equal to V0 sine omega t, and this is equal to Q0 sine omega t. When we say that current leads voltage by phase angle 90 degree, we should remember that in a capacitor, the current reaches its peak value before the voltage does. Alternating current changes direction regularly. This changing direction allows alternating current to move through a capacitor. The capacitor charges and discharges continuously because of the alternating nature. Remember that the reactance is equal to measure of opposition of capacitance against flow of alternating current. Reactance is how much a capacitor resists the flow of alternating current. It is similar to resistance but specifically for capacitors and alternating current. Exactly like resistance, reactance is also measured in ohms. The formula for capacitive reactance is this. Remember that here Xc is the capacitive reactance, Vrms is the root mean square voltage, Irms is the root mean square current, F is the frequency, C is the capacitance, omega is the angular frequency which is equal to 2 pi f. From the above formula, we can say that the frequency is inversely proportional to the capacitive reactance. So when the frequency increases, the reactance decreases. In a circuit with only a capacitor, the voltage reaches its peak value after the current does, which means the voltage lags behind the current by 90 degrees. Now let's discuss the alternating current through inductor. An inductor creates a magnetic field when alternating current flows through it. Because AC is always changing direction, the magnetic field changes too. This changing magnetic field creates a specific inductive effect. When you apply a voltage to an inductor, it generates a counter voltage or back EMF that opposes the change in current. Formula for back EMF is given by this. Here EI is the induced EMF, L is the inductance, del I over del T is the rate of change of current. We stated that in a capacitor, current leads by phase angle 90 degree, but in the case of inductor, the current reaches its peak value after the voltage does. This means current lags behind the voltage by 90 degrees. Inductive reactance is how much an inductor resists the flow of alternating current. It depends on the frequency of the AC and the inductance of the coil. The formulas for inductive reactance are these. Here XL is the inductive reactance, Vrms is the root mean square voltage, Irms is the root mean square current, F is the frequency of the AC, L is the inductance, and omega is the angular frequency. From this formula, we can say that frequency is directly proportional to inductive reactance. So when the frequency increases, the inductive reactance increases. In a perfect ideal inductor, the energy stored and the magnetic field is returned to the circuit. There is no loss of energy as all the energy is stored and then released back to the circuit. And at last, we can say that in the circuit with only an inductor, the current reaches its peak value after the voltage does, which means current lags behind the voltage by 90 degrees. That's all for this video.